All right, hello. Today we start working with chapter 6, which deals with irrational and complex numbers. So, the first thing we'll do is work with irrational numbers. Now, you've done some of this in Algebra 1. We'll just take a little bit farther. And then the second part of this unit, we'll talk about complex numbers and start working with I. And then this will allow us to get into the meat of really what we learned in Algebra 2, which is how to solve first any quadratic equation and then any polynomial equation. So, first thing here, irrational numbers, right, are mainly numbers like pi, numbers that have decimals that do not end or don't repeat. You can't write them as fractions, and numbers like pi that we see a lot in algebra are square roots of non-perfect squares. So we all know our perfect squares. If we square 1, we get 1. We square 2, we get 4. We square 3, we get 9. So numbers like 1, 4, 9, 16, 25, and so on are perfect squares. And when we have a square root, it's technically called a radical sign, right? So here I have a radical sign. The number inside is called the radicand, and this little number up here that we'll put is called a root. Now, you mostly work with square roots in Algebra 1. When it's a square root, we don't even put a number there. But if it's a cube root, we put a little 3 there, and so on. Simplest radical form is something we work with. Now, when we have radicals, since they're decimals that don't end, don't repeat, we can't get an exact answer. So we always simplify them as much as we can. Now, the rules for simplest radical form are on page 266 in your book, but here are the main things. First, no radical contains a factor that has a perfect nth power. So when it was square roots, there couldn't be any perfect squares inside the radical other than 1. Second, every denominator has been rationalized. What does that mean? Well, no radicand is a fraction, so you can't have a fraction inside a root or a radical sign. And no radical is in the denominator. So I'm going to do a quick review of a couple things you would have done in Algebra 1, then we'll take it where instead of square roots, we have other roots, like cube roots and fourth roots and fifth roots. So let's say I had the square root of 75, and I'm asked to simplify that. I think of my perfect squares, and I start with, first of all, I take half of this number, which would be 37 and a half, and I start checking all the perfect squares from that down. So I would see if 36 went in, it doesn't, then I would go to the next one, which is 25, which obviously goes in. I make this a square root of 25 times 3. 25 is a perfect square, so I can take its square root. That goes in front of the radical because the square root of 25 is now 5, not the square root of 5, and the 3 stays inside. Take notice the 3 doesn't have any perfect square factors other than 1, so we're done. Sometimes you had fractions, so the square root of 8 over 25. We can break this into the square root of 8 over the square root of 25. Square root of 25 is 5. Now, can I simplify the square root of 8? Sure. That's the square root of 4 times 2 becomes 2 root 2 over 5. So there's no fractions in my radicand. I got rid of that here first. Sometimes you can maybe even simplify the fraction if possible. And then I don't have any radicals on the bottom, but always simplify even that one in the numerator. Let's say we had something like this, 15 over the square root of 3. So we don't have any fractions in here, and we can't simplify this, but we can't have any radicals on the bottom. Well, if I would take the square root of 3 times the square root of 3, that becomes the square root of 9, which equals 3. So to get a square root of a number to become itself, if I take the square root of x times itself, the square root of x, I just get x. So I multiply this bottom by the square root of 3. I no longer have a square root on the bottom. I must do the same thing to the top. So I get 15 times the square root of 3. Now, if I can simplify numbers that are not radicals here, 15 and 3, I do that. So I can divide, and I just get 5 root 3. So Simplifying here, some review. Let's do one more. Let's erase that over there. 9 times the square root of 5 over 27. Now, 27 is not a perfect square, but I can simplify it. First of all, I can make this the square root of 5 over the square root of 27. But I'm going to just do this right away. 27, I can make that 9 times 3. Right? This 9, since we have a fraction here, I'm going to make the 9 a fraction a while. So I have the square root of 5 on the top. On the bottom, I have 3 times the square root of 3. So I can't have the square root of 3 on the bottom of this fraction. So to get rid of it, I'm going to multiply by that square root. So let's multiply across here. So I have 9, and the square root of 5 times the square root of 3 is the square root of 15. On the bottom, I have 3 times the root 3 times root 3, which is another 3. So this becomes 9 root 15 over 9, so the 9's cancel out. And my answer is the square root of 15. So you would have worked with square roots before. So, make sure that worked. That's just review. I do want to do one more type, so let's quickly do this one. The square root of 96 over the square root of 3. Now, I could rationalize this right away by multiplying by a square root of 3, but if I can do this division, 96 divided by 3, I could do that right away. And 96 divided by 3 is just 32. That is the square root of 16 times 2, which becomes 4 root 2. So you can use our quotient property here backwards too. All right, now let's go to higher roots. Let's say I write down some perfect cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed, 7 times 7 is 49, 49 times 7 is 343, and so on, right? So there's some perfect cubes, and you can just keep going if you'd like, because of time I'm not. So let's say I want to simplify a perfect cube. Let's say it's the cube root of 135. So I got to find one of these perfect cubes that divides into it. Right? So, your calculator is going to be helpful. I wouldn't take half anymore because we're doing perfect cubes. But what I do is start dividing 135 by some of those. And I find out that if I divide it by 27, I get 5. So this becomes the cube root of 27 times 5. The cube root of 27 is 3. And that's times the cube root of 5. So I can simplify cube roots, right? The same way we did perfect squares. Now let's say we have a fraction, the cube root of 1/4. Right? So when we had square roots, we would just make the bottom, multiply by itself. Here you don't want to do that. You want to make the bottom one of these perfect cubes. Well, 4 could become 8, it could become 64, it could become 216, but we picked the smallest one, 8. So I take this fraction, 1/4, and to make the bottom 8, I multiply by 2, but I got to do the same to the top. So this becomes the cube root of 2 over 8, which means it's the cube root of 2 over the cube root of 8. I break it into 2 cube roots using my quotient property. And then the cube root of 8 is 2. So my final answer is the cube root of 2 over the number 2. So again, if this is a fourth root, I'd want to maybe write down some perfect fourth powers by just taking the numbers 1, 2, 3, and so on to the fourth powers and writing them down and trying to make these fourths, perfect fourths, perfect fourth powers. So let's do a fourth root. Let's say it's a fourth root of 162. So again, I could 1 to the fourth power, don't really need it. 2 to the fourth power will be 16. And 3 to the fourth power is 81. And I think, bingo, I hit it there, right? I make this 81 times 2. The fourth root of 81 is 3. And it's times the fourth root of 2. Let's even go farther here. Let's say I have the sixth root, or the fifth root, I should say. And let's make this 3 over 32. Right. So let's list some powers of 2, because 32, might be one of those. 2 to the first power is 2. 2 to the second power is 4. To the third is 8. To the fourth is 16. To the fifth is 32. So this is a perfect fifth power. So this becomes a fifth root of 3 over the fifth root of 32. So the bottom just becomes 2. So it's a fifth root of 3, looks a little sloppy there, over the number 2. What if this was, let's say, 8 here? Well, I would want to make this 32 now, so I would multiply it by 4 over 4. So then I have the fifth root of 12 over the fifth root of 32, or the fifth root of 12 over the number 2. And sometimes we could deal with some decimals here, so let's just do one of those quickly. Let's say I have the cube root of 0.064. So why don't we think of this as a fraction? So let's see, after the decimal point, it goes tenths, hundredths, thousandths. So this is really the cube root of 64 over 1,000. Right? Isn't 10 to the third power equal to 1 with 3 zeros after it, right? So that is a perfect cube. So this becomes the cube root of 64 over the cube root of 1,000. Now, let's see. So the cube root of 1,000 is going to be 10. 64, right? 4 to the third power equals 64. So I can take the cube root, that becomes 4. So since I was given a decimal here, I'm going to actually just write this as 0.4. You could have plugged that in your calculator too. Okay? Under the math part, you can get roots. If it's a cube root, it's right there. Now, you can't do that when it's not decimals, put it that way. But when I go to math, the cube root is the fourth one. The fifth one is any root. You just got to put the number for the root in there first. Okay, so hopefully those examples will be helpful. Again, if you're struggling, don't be afraid to contact me during Zoom office hours. Have a wonderful day.